Hello, this is Mr. Gilmore with the 3.5 Angle Side Angle Triangle Congruence. We're going to introduce our third triangle congruence shortcut with using angle side angle. Now this one is going to be a theorem, which means we will have to prove this one. So let's state what the angle side angle triangle congruence theorem states. It states this: if two angles and the included side of one triangle equal two angles and the included of a second, then those triangles are in fact congruent. We've seen this vocabulary word used before, included with the use of angles. Now we're going to use it for the use of sides. What this means is that the side is the one that's sandwiched between the two pairs of equal angles. Let's have a look at the diagram. So what this theorem states is if triangle ABC and triangle RST, we have these two triangles such that angle A and angle R are equal, angle C and angle T are equal, and the sides in between those, which means they're the included sides, then these two triangles would have to be congruent. So notice that AC and RT are marked as congruent. Let's go ahead and set this proof up. We're going to actually now prove that these two triangles are in fact congruent. So we're given, right, this pair of equal included sides, AC and RT. We're given that angle A and angle R are equal, and we're given that angle C and angle T are equal. Let's prove now that these two triangles, triangle ABC is congruent to triangle RST. Now we're going to take Euclid's approach in proving this, and it's absolutely an ingenious proof. See, if we were to jump into this directly, we wouldn't get very far. But what we can do is use our properties and method of indirect proof. So we're going to assume the negation of our proof statement, which really means we're assuming that triangle ABC is not congruent to triangle RST. But here's the big picture about congruence. Just because we assume it's not congruent doesn't mean that every single part does not match up. All we have to do is assume that one part does not match up, which then means they wouldn't be congruent, right? We have to have identical lists. So Euclid, instead of assuming they're not congruent, he assumes that there's a second pair of sides that are not equal to each other. So let's take a look at that. So we go back to our two triangles, triangle ABC, triangle RST. What we're going to do is we're going to pick a second pair of sides. We already have one pair of equal sides, AC and RT. We're going to then pick a second pair. We're going to choose AB and RS. Those are the two sides. Let's assume that AB is not equal to RS. Okay, let's assume that they're not equal to each other. And if we assume that, then yes, we have assumed that the triangles are not congruent. So again, we're jumping into our indirect method. So what does this say if we then assume that AB is not equal to RS? This says then by the law of trichotomy, one of those sides must be greater than the other. So we have two conclusions. Either AB is greater than RS or AB is less than RS. Now here's the thing about this proof. We're going to stick with the first, with AB being greater than RS. However, if we were to say that AB was less than RS, the proof of that one would be practically identical, only changing in minor detail. So if we prove it for AB is greater than RS, then we'll get away with also showing that AB is AB less than RS would be somewhat similar, just changing minor detail in our proof. So what we can do then is if we have assumed that AB is greater than RS, that means think about two pieces of string. If AB is a piece of string that's longer than RS, then we can actually cut that longer piece of string down to equal the shorter string. So if AB is longer than RS, then we can then measure to a point Z such that AZ is equal to RS, right? Because we've assumed AB is greater than RS, which means AZ will have to be equal to RS. Now what we're going to do is look for some congruent triangles. So let's take a look at breaking down our reduction here. So same diagrams that we saw on the same last page. We now have this new triangle ACZ. As it turns out, we actually have a pair of congruent triangles now. Let's take a look. We have marked AZ equal to RS, right? Because by our construction, we can then cut AB shorter to the point Z, which means AZ is equal to the length of RS. Because remember, our assumption is that AB is longer than RS. We, from our given, have that angle A and angle R are equal, and we have our sides RT and AC are equal, which means, guess what? We have a pair of congruent triangles by side, angle, side. So why do we know CAZ is congruent to triangle TRS? Which, if we take a look at CAZ, it's this smaller triangle right here. Right, there's CAZ, which is actually then going to be congruent to this triangle RST. And that is, again, true by side, angle, side congruence. Which means once we've invited congruence to the party, we can now begin to invite congruence's best friend, which is in fact our best friend, CPCTC. So now I can claim that angle ACZ, which is this angle right here, okay? Now I have to be very careful here. It stops right there, right? It's not going to go any past there. There's our angle ACZ. It's got to be equal to angle T, and here's why. Those are corresponding angles, and by our corresponding parts of these two congruent triangles, we know them to be equal, because if we take a look, angle T matches up with that angle C there, which means it's angle ACZ. Those are corresponding angles. Now, we also know that angle T and angle C are equal to each other. Why is that? Well, actually, if we go back and look at our setup, that's from our given. All right, we know that angle T is equal to angle C by our given, which then what follows about angle ACZ and angle C? Well, let's take a look. Angle ACZ, so when I say angle C, I'm referring to the entire angle C. So when I say ACZ is equal to to the measure of angle C, well, that follows because take a look at our step 2 and our step 3. ACZ is equal to T, and T is equal to angle C, which means angle ACZ is equal to angle C. And that's just by transitivity of equality. Now, here's the big picture, though. Take a look at what we just said. We just said that angle ACZ is equal to the entire angle C. Wait, what? We can't say that. We just said in our last statement that the whole is equal to the part, but that can never happen. That is our contradiction. The whole and the part will never be equal to each other. The whole is always greater than the part, which means we have enough to leverage out our assumption. Now, our assumption, remember, was that AB is greater than RS. Well, that can't be true now, because if we did assume that, we would hit this contradiction. So what's our conclusion then? Well, since we assume that AB is not equal to RS, and that means we toss out both AB is greater than RS, that one can't work, and likewise, if we had assumed this one, we would have hit the same exact contradiction, which means it can't be that one. So there's only one thing left remaining, and that is AB has to be equal to RS. So what does that mean for us? Well, that means AB and RS have to be equal. Well, what that does is it produces a second pair of equal sides for us. So take a look at what we have. Side AC and side RT are already equal. We have angle A already equal to angle R. Hey, look, that's side, angle, side, side, angle, side. So now we know that triangle ABC is in fact congruent to triangle RST by side, angle, side. So what's interesting about this proof is we use a little bit of both indirect method and direct method. We first use indirect method to prove that AB and RS have to be equal. That's what we did here. But then we finish off with a direct method. Now that we know that AB and RS are equal, then we can use our reason of side angle side congruence to show that triangle ABC and RST are in fact congruent. So now we have a new triangle shortcut. Let's actually use that triangle shortcut in our proof here. So we are given that BD bisects both angles ABC and angle ADC. Let's prove that triangle ABD is congruent to triangle CBD. So I'm going to go ahead and set up my two column. This is actually not going to take us very long. Very nice, sweet to the point proof, actually using angles, side angle congruence. We start off with our given. BD bisects both angles ABC and ADC. So from my given, I know I've got actually a dual angle bisector. What that does for me is I can state actually two things. Let's start at the top with angle B. The measure of angle ABD is thus equal to the measure of angle CBD. And I get that here from the top. And I know that because it satisfies the definition of angle bisector. Okay, what else can I say? Well, I have BD also cutting angle ADC in half as well. So I can say in the exact same step that the measure of angle ADB is equal to the measure of angle CDB. And that's the same reason, definition of angle bisector. So I know that these two angles here have got to be equal to each other. So now I have two angles of one triangle equal to two angles of the other. If only I had their included sides equal. Well, as it turns out, they share the side BD. So BD is equal to itself by our good old property of reflexivity of equality. That gives us an equal pair of sides. Not just that, but the equal pair of included sides, which thus means we can claim triangle ABD to be congruent to triangle CBD by angle side angle congruence. So a simple proof actually applying our new congruence shortcut angle side angle. Now, we have to talk about something. You're going to probably get a little giggle on this next slide. Okay, we have to talk about something. We've seen shortcuts for side angle side, side side side, and angle side angle. But we're also going to have to consider all the other sorts of combinations of angles and sides that we can actually pair. So the next question is, are there other relationships that don't work? As it turns out, the answer is yes. So now with this slide, I always get this question every year. What about angle side side, Mr. Gilmore? Is that one of the triangle congruences that we actually can use? No, we can't actually use angle side side as a triangle congruence, even though it is 3, right? We've been talking about shortcuts with using our magic number 3. But it turns out angle side side, right? Oh no, there's a bad word on your slide, Mr. Gilmore. The angle side side actually has a counterexample to it. So in this diagram below, let's consider two triangles. Let me mark the first triangle for us. So the first triangle is triangle ADB, this triangle right here. And the second triangle, let me actually change color for us so we can see this other triangle, CDB, which is this entire triangle here. These two triangles are actually our counterexample. Here's why. If we take a look, both triangles share an angle, angle D, which means they do have the angle in common. And both triangles share a side in common, which is this side right here, BD. So they have the angle, they have a pair of sides, and as it turns out, they also have a second pair of equal sides right here. So that's actually angle side side, right? Look at that. Angle, side, side, angle, side, side. But are they congruent to each other? No, okay? And we can use a diagram as a counterexample to prove something wrong. So angle side side, unfortunately, is not a triangle congruence. What about angle, 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 right? If we knew that all three angles of one triangle were equal to all three angles of a second, does that actually prove the two triangles are congruent? No, okay? It does not. It does not prove congruency. As you can see that these two equilateral triangles actually have all three angles of the first equal to all three angles of the second. However, their sides may not be the same. I could have, let's say, sides of 3 here and sides of 7 over here. Well, no way are those two triangles congruent. It does, however, prove something later on. If we look ahead to chapter 7, we're going to find that if we have three angles of one triangle equal to three angles of another, we can't call them congruent, but we can use another term we're going to see later on called similarity. So we can actually prove them similar to each other. So if we then put all of our congruences kind of together, this like checklist of our congruence scorecards, we find that side angle side, yes, checks, it works out. That's one of our postulates. We proved side side side, that was our theorem, and then we just proved today angle side angle theorem. So then there's another combination. What about angle angle side? All right, what about angle angle side? Well, that actually is a theorem. We're going to prove that in chapter 4. We don't have enough tools right now to prove angle side. We'll prove that in chapter 4. And then we also considered our angle side side and angle angle angle. Those unfortunately do not work as well. So this is really all the combinations that we can make with angles and sides to form our shortcut of 3. And as we see, we're going to add, right, angle angle side later on. And there's also a special case, which we'll talk in chapter 4. There's also another special case that proves congruence. So now we are at the end of our lesson 3.5. Please be sure to work on the 3.5 homework assignment, and if you do have any questions, email me about that. Be good and do good.